Okay, so that's last chapter. Chapter 4 is about relationships between data. And so we're going to be dealing with a lot of paired data, so x and y values. So remember, x values go left to right, y values go up and down. X values will always be the first in the pair, y values second. So let's review lines and sets of points together, make lines. Let's talk about a positive slope rises from left to right. It could be steep. It can be not that steep, but from left to right, it always goes up. All of these are positive slopes. Negative slopes are the opposite. They go down from left to right. And same rules apply. It can be steep or not. They're all still negative slopes. So for our paired data, the response variable, y, is the variable whose value gets explained by the explanatory or predictor variable, x. So we've got an input that's trying to explain the output, essentially. A scatter diagram is a graph of all the points. So you have a bunch of data. If you plot them all as points, that creates a scatter diagram. So let's look at what some scatter diagrams can look like and what we can conclude based on their looks. A is a linear positive slope because it's going up from left to right. B is kind of a linear negative slope because it's going down from left to right. C is non-linear, but there is a pattern. D is also non-linear, but there is a pattern. It kind of looks similar to linear, but there's some dip in the middle. And E, there's just no relation. Everything's all over the place. So when I say positive, when someone says positive correlation between two variables, they're saying that if one increases, the other increases. Similarly, if one decreases, the other decreases. Negative correlation means they're moving in opposite directions. If one's getting larger, the other one's getting smaller. So we'll look at what we expect to be a positive and a negative next, and we'll make some scatter diagrams. So construct a scatter diagram for the data obtained in a study of the hours studied for a specific exam and the grade on that exam. So let's plot our points. So we've got 682. Studied 6 hours, got an 82. Plot the point. 258. 370. 898. 160. 575. Now, generally, it looks like as we go from left to right, so as our x value increases, what's happening to our y values? They're also increasing. So what kind of relationship is this? Looks like it's a positive correlation, which we would expect to be true, right? We would expect that as you study for more hours, your exam grade should go up. Now, that doesn't mean that everyone who studies a lot is going to get a higher grade than everyone who doesn't study a lot. Different requirements for different people, depending on the subject matter. But it's clear that in general, the more you study, the better you should do. What about constructing a scatter diagram for the data obtained in a study on the number of absences in a course and the final average in the course? What do you think? Do you think the more if absences go up, what do you think is going to happen to your course grade? You probably have an idea, but let's plot the points and see if the data suggests otherwise or confirms your suspicions. 5 absences got a 50. 1 absence got an 85. 2 absences got a 68. 0 absences got an 80. 0 absences got a 95. 3 absences got an 82. 10 absences got a 40. Okay, so this one isn't perfect, but what do you notice as your x increases from left to right? Generally, your grade is going down. This means as one is increasing, the other is decreasing. So this is the kind of thing that would be a negative correlation. And it looks probably linear, or somewhat close to linear. Both of them looked somewhat linear. Okay, but we would like to have a mathematical way of determining exactly how related two different things are. And we've got what we call R, or the relation coefficient, the population correlation coefficient as well. So the linear correlation coefficient is a measure of the strength and direction of the linear relationship between two quantitative variables. So strength and direction means that how much of a linear relationship is there percentage-wise, and direction means positive or negative. And it's this equation, R equals the sum of all xi minus x bar over the sample standard deviation of x times y minus y bar over the sample standard deviation of y, all divided by n minus 1, where n is the number in our sample. X bar is the average of our x values, y bar is the average of our y values, and s of x and x of y is the sample standard deviation. So if you remember back to chapter, I think 3, when we did standard deviation, we're going to have to do that sometimes in our calculator as well. Now, that's a lot to take in, and we'll do a problem in the next video. So let's talk about some of the attributes that this can have. Okay, so the linear correlation coefficient is always between -1 and 1, including -1 and 1, because this is like a ratio. If you think about what does 1 represent, I mean, it represents 100% in decimal form. But you can't go above 100% linear relationship because that's positive, full-on linear relationship. -1 would be a negative 100%, so fully negative linear relationship. So if you get exactly +1, then it's a perfect positive linear relationship. So a very, very, very perfect positive correlation. If R is -1, it's a perfect negative correlation. Similarly, the closer to +1 you get, the stronger indication of a positive relationship. The closer to -1 you get, the stronger indication of a negative relationship. If your R is a small decimal close to 0, that means there's not really any evidence of a linear relationship between both variables. So we would say there's probably no linear relationship. Doesn't mean there's no relationship, just not a linear one. The linear correlation coefficient, that R, is unitless as far as measures go. So it doesn't matter what x and y are, and like what they represent, it has no bearing on R. And the correlation coefficient is not resistant. So if we talked about this, things like the mean and standard deviation were not resistant, whereas the median and the interquartile range were more resistant. If there's an observation that's way off from the rest of the data, it can dramatically affect the R value. So this is the visual representation of a perfect positive linear relationship. Everything's in a line. Strong positive, so this is at R equals 0.9, which is close to 1. There's a little bit of a scatter, but it's mostly up increasing. A moderate positive linear relationship, so you can see the dots are a little more all over the place, but generally it still goes up from left to right. Perfect negative, it's the same as positive, only it's going down. Strong negative, -0.9, similar to B, but it's going down. F is similar to C, a moderate negative relationship. When you have an R close to 0, no linear relationship, it'll look like things are all over the place. But that's not the only situation. There can be no linear relationship when it does have a pattern, but it's just not a line. So we will calculate R one time by hand and then talk about how to do it in the calculator in the next video.